mass and is more stubborn, gravity pulls on it that much harder to make sure it accelerates the same as everybody else. You can see it's right in the equation, by the way. If g is the same for everybody, then things that have more mass will get pulled harder by gravity. I am not going to illuminate that whatsoever at the moment. We'll actually come back to this around homework 6, and we'll really get to figuring out what's going on with gravity. Right now, all I'm trying to construct is kind of just a ad hoc kind of get me the right answer, get me the right amount of newtons. So for us, the force of gravity at this point is no more than the force that causes a particular acceleration to everything. Okay? So because we're really just trying to construct something that works and gets us the right answer, we wind up in some strange situations. So for instance, if we have one of these objects, this object, it will actually accelerate at 9.8 meters per second squared downward. If gravity is the only force, well, gravity is the force that causes this acceleration. There's no other forces, so it will have that acceleration. But we even use this formula, mg, in situations where it seems like we shouldn't be using it. I'll give you an example. We have a mass sitting on a table. We know the force of gravity pulls on it. What is the size of it? Well, the size of it must be however much force such that it would give it that acceleration. And yet, there is obviously another force here, which we'll introduce later. It's called the support force or normal force. And it actually kills that force. And so what is the actual acceleration of this thing? 0. It has no acceleration. So it seems kind of strange. We are using the gravitational acceleration even though it is not accelerating at all. Because in this case, what we're doing is we're saying we're inferring the force by how much acceleration it would cause if it was acting alone, even though it's not acting alone and the acceleration is different. It's 0. Okay? So that is the price we pay for a completely just get us the answer without knowing anything else. So in this case, again, we infer the force of gravity by knowing the acceleration it would cause if it acted alone, even though there are other forces and the acceleration is actually not that at all. Okay? This allows us to punt one more unit down the road. What's going on with gravity? It just gives us something to work with. It allows us to infer the pull of gravity, even though we don't really know why it is that. It just allows us to infer it by knowing what acceleration it would cause if it's acting alone, okay? Even though it doesn't often act alone and the acceleration is not g, okay? Are there any questions on that before we move on to the tension? Okay, so let's do the tension. Grab a string from somewhere. Here's the string. Okay, so tension. How much tension is in a rope? It really depends. String can be tight, right? Have a lot of tension. String can be loose. Have a little bit of tension. Tension can even be 0. Tension can be so tight that it breaks. There is a common tension at which ropes will break. There's no silver bullet here for that. The tension, the size varies. It really depends on what it's being asked to do. You have to infer that from context. If you have some rope that's doing something and it's not breaking, you can infer how much tension it's applying. But there is a rule of thumb for direction that we can at least count on. There's a certain one-wayness to a string. You can pull something with a string, right? But you are significantly less effective pushing something with a string, okay? There's a certain one-wayness to the force, right? So what does that mean, practically speaking? If you have an object and you have a string that's attached to it, the force always pulls, it never pushes. So you should have that force is pulling and not ever pointed like this. Okay? So tension always pulls, it never pushes. It's along the rope, always pulling, never pushing. Okay, so that gives me two forces to play around with. So let's do a problem where we go back and we look at the, incorporate these two forces, vector addition, and your homework 4 problems are, the homework 4 is going to be full of the type of problems just like the one I'm about to do. Okay, any questions before I start the example? Okay, let's do it. So here's my situation. I have a sign. I'm opening up a new store. I want to put a sign outside. Okay? I'm going to have some kind of mass, and I want to hang it. Let's say, either because of some kind of environmental restrictions, or I just want to try to be clever, I'm going to hang it like this. I'm going to attach one rope horizontally to a wall, and the other one, I'm going to attach it at diagonal to the ceiling. I'll call this rope 1 and rope 2 just so I can keep them straight. I'll say the mass of my sign is 1 kilogram, and this one that's going diagonally, let me say that's going at 30 degrees. So those are my givens. Put them on the list here, givens. Generally, if I want to keep track of what's given, I'll mark it as a check mark, as I've been doing. Here's what I want to ask. What is the size of the tension in each string? And notice here, by the way, that I've left the vector hats off of those on purpose. I want to know the size of those tensions. The directions is not that hard. The sizes is the part where we have to really start calculating. So here's what I'm going to do. I'm going to knock this problem out, kind of talking through it. And then after I finish it, I'm going to congeal those steps down into a problem-solving strategy. This is what I was talking about last lecture. It's kind of a more nuts and bolts version of how to attack these problems. So the idea is, if in general you want to identify forces, combine them, any net force leads to acceleration, any acceleration ties into kinematics, this is just going to be a recipe that walks you through it, even if, for instance, you're working that thread of logic from left to right or right to left or coming in somewhere in the middle, right? We want a recipe that is immune to having to do the steps in a certain order. I don't want to write down this problem-solving strategy right away because it's very much overwhelming. So I want to kind of informally go through it in this problem, and then I want to formalize it into a series of steps. And this recipe, this 6-step recipe, you can apply it. If you don't stray from it, it'll solve every problem on homework 4 and 5. Okay? The problem is just getting you to follow it and not stray from it. Okay? So let's go ahead and do it. First things first, I'm going to pick the sign, and I'm going to focus in on the forces that act on it. There's a force of gravity that pulls down on it. Gravity always pulls down. But of course, it's not in free fall, which means that it has other forces. And those other forces come from the ropes. And I remember that tension always pulls, never pushes. So I make sure to direct those two forces away. Okay? So one rope pulls the object to the left, the other one pulls it diagonally right and up. So, as far as the net force goes, that's not really what I'm interested in here because I know what the net force is. The net force on this sign is, hopefully, if nothing goes wrong, is what? 0, so the acceleration will be 0, so it stays where it is, right? So in this problem, my goal is not to take known forces and to calculate an acceleration. My goal is, I know the acceleration, I'm going to work backwards to figure out what the forces must be. So it's kind of like going in the opposite order. I'm not taking known forces and calculating the acceleration. I'm taking a known acceleration and working backwards with the forces. It's the same thread of logic. It's just whether you work it from back to front or front to back. Okay? So let's figure out how it is then. What are these two forces such that it would hold this thing in place? Now there's diagonaling forces here, so in order to make it more digestible, I want to split it up into x and y axes. So I want to be able to think of the horizontal and vertical as independent things. And so if I look at my forces, my force of gravity is entirely vertical. That's in the minus y direction, as I've said it. The tension is entirely in the minus x, but the tension, T2, is diagonal. And so I want to break it into components. So I want to break it up into T2x component and T2y component. So I go ahead and do that, identify they're both positive components, and I go ahead and do it. And of course, I can express both components in terms of the hypotenuse, the total amount of force, times the appropriate trigonometric function, cosine or sine. At this stage, I would highly advise you to do what's called a free body diagram. And a free body diagram is basically freeing the object or body of interest and putting it by itself, freeing it from its environment so we can look at it in isolation. And then what I would do is I would recommend that you put in all the forces, but already resolved into the two axes. So let's go ahead and do that. We've got the force of gravity. Its size is mg, and the direction is minus. Notice here, what's in the parentheses is the size. And I can represent the direction as minus because I've now at this point chosen axes, so minus has meaning. I'll put this other one over here. This is minus T1. Again, notice the same thing. In parentheses is the size, and T1 written without the vector hat is the size. And then the minus on the outside to represent minus x. And then the others, go ahead and do those. Like that. So I'm basically resolving that diagonal force from the second rope. I'm resolving it into a horizontal and vertical pull. And again, remember that what's in the parentheses is the size only. And then what's in the front is the direction, which can be represented, if we're talking components, as plus or minus. It just means it's plus or minus relative to the axis that I've set. So what we're looking at here is looking at the object, and we have two completely independent tug-of-wars going on, one in the horizontal direction and one in the vertical. So we imagine there's a leftward force and a rightward force, and if neither one wins, then the net force in that direction is 0 and it stays put. Then we also have two things pulling on it vertically. One pulls down, the other one pulls up, but if neither of them win, net force in the y direction is 0 and it stays put. It stays at rest, no acceleration. So basically, we already know this is going to kill this, this is going to kill this. And if all of those forces kill each other, then there's no acceleration. It stays doing what it's already doing, inertia, the concept of inertia. If it's at rest, it'll stay at rest. Now this is basically already telegraphing the solution, but let's go ahead and write it out. So we talked about the process of vector addition. F net x equals max. Looks like this. There's my x equation, and I'll leave a couple lines, and I'll do my y equation. And if there is any force left over, that leads to acceleration along that axis. So those are your generic equations. And then, of course, we can just start filling in. We already know there's no acceleration in either direction. This thing just stays put if all goes well. We're trying to figure out the tensions that are necessary for it to not go anywhere. And then we just start putting in our components. So in the x direction, we have plus t2 cos theta. We have minus t1, and those add to 0. So again, notice how this is working. The sign is out front already, so there had better not be a surprise negative sign coming from within the parentheses. The signs are taken care of on the outside. What's in parentheses is the amount. It should never have a negative inside, okay? Likewise, for the other direction, we have one upwards force and one downward force. Remember, the signs are on the outside, so what's in parentheses better not have a surprise negative sign. And this is where I'll guarantee you someone will make this mistake. They'll put in G is negative 9.8, and that negative kills this negative, and suddenly your force of gravity is pulling upward, okay? The minus is out here because the minus is not in here. The minus is on the outside because G is not negative, okay? All right? So let's go ahead and finish this up. T2 cos theta equals T1, which is to say those two forces have the same size. Same size, one being plus and minus, adds to 0. Which we kind of could have said already, right? Looking at this, if you start to get quick with this stuff, this must match this, if those are going to cancel, right? If the left and right forces are going to cancel each other, the two forces have to have the same size in opposite directions. Just like over here, T2 sine theta equals mg. Those two forces have to have the same size. All right? So we have not one, but two equations that have to be satisfied in order for this sign to stay where it is. We have to have both the vertical and horizontal forces all are canceling. So let's go over here. The second one seems a more promising place to start. Because I can solve for T2 directly in terms of things that I know. So T2, that's the tension in the second rope. I know M, I know G, I know theta. So I go ahead and I just plug those things in. I was given the mass is 1 kilogram, the angle is 30 degrees, and G is always known. It's 9.8 meters per second squared. If you do this, you'll get a numerical value. All right? And let me go over here. Now T1 from the other equation is equal to T2 cos theta. Now if I'd started there, I would have thought I was stuck, right? Because I have both unknowns, T1 and T2, there. There's no way you can squeeze two unknowns out of one equation. But, of course, now I know T2, so I just put it in, right? In fact, let me be a little fancy and put in the expression. I'll tell you why you might want to do that. I can consolidate this is equal to mg cotan theta, or mg over tan theta, whatever you want. Or, of course, we can just get a number, and the number is 17 newtons. Those are my answers. There is no other pair of tensions, T1 and T2, that would satisfy the situation. T1 must be 17 newtons. The tension in rope 2 must be 19.6. Let me try to convince you why that must be. Okay? Why is it that no other pair of forces is possible in this situation? I'll go back and put in the numbers. Let's work out what m times g is. I have 1 kilogram times 9.8 meters per second squared. So we know that gravity gives everything an acceleration of size 9.8 meters per second squared, and this particular thing happens to be 1 kilogram, which means in order to be satisfying Newton's second law, gravity must somehow pull on that with 9.8 newtons. Of course, it doesn't really accelerate at 9.8 meters per second squared. It's because it's being held up. But we infer the force of gravity that way. So the gravity is pulling down at 9.8 newtons. And we know that, again, because it would accelerate accordingly should the ropes break. Well, if that's the case, how much force must we use to hold it up with? Same amount, right? 9.8. So this had better be 9.8 newtons as well. Well, here's the thing, though. Remember that T2 was not all being used for this purpose. T2 is on a diagonal, which means part of its resources are directed to the side, and only part of its resources are up, right? So out of this entire force, some of it's to the side and some of it's upward. So we don't get the whole force. We only get the whole force times sine of 30 is how much we get upward. And you can work out how much force must be in T2 in order for T2 times sine of 30 to get you 9.8. Of course, that's 19.6. So 19.6 newtons must be in that rope, so that 19.6 sine of 30, which is the vertical part of that force, make sure to fulfill your vertical obligations, which is to hold up 9.8 newtons. But if you have 19.6 newtons in that rope, not all of it goes vertically. Some of it goes to the side. So let's find out. How much does it get you to the side? Well, 19.6 times cosine of 30 means that you also incur 17 newtons to the side. So how much does T1 have to do? It needs to cancel that 17 newtons, right? So at no point did I have any choices, right? If the ropes are configured the way they are, I had no options whatsoever. If the ropes are going to do the job both vertically and horizontally that they need to do, there are no other values of T1 and T2 that can satisfy these equations. In fact, this is your classic 2 equations and 2 unknowns, right? One of the things we put on the math exam, simultaneous equations. So 2 equations has a unique solution of 2 unknowns, okay? Are there any questions on that? Okay, so let me say a few brief words about symbolic solutions. This is something we'll move more to, okay? In math, the thing that gets most in the way of math is numbers, okay? Real math does not have any numbers, okay? Let me explain. In this situation, if I plug in 1 kilogram of 30 degrees, immediately my solution is only valid for that mass and that angle. It's a much more sophisticated way to ask what is the answer for a sine of mass m, any mass m, and for any angle theta. Okay? So this answer and this answer, oops, that's, yeah. That's a lot more powerful solution, because I could give you 17 different sets of m and theta, and you have the equations ready to roll. it's to set up an Excel spreadsheet with all your different m and theta values, and then you use these two equations to find T1 and T2. It's a much more powerful solution. Rather than being beholden to a particular set of numbers, you have solved this for any mass and any angle, okay? So that's symbolic solutions, okay? So symbolic solutions, your answers are in terms of given variables. They're not numbers. And I guess I should mention, thrown in there, known constants. So for instance, if in a problem I were to give you m and theta, but the number delivery truck was running